class, this is Patrick. We left off midway through chapter 5. Picking up here, we were talking about uneven multiple cash flows before we left off, and we're going to pick up right at that point. So, uneven cash flows are defined as a series of cash flows where the amount varies from one period to the next. We've already dealt with payment. This is a term that designates an equal cash flow coming at regular intervals. Cash flow, or CF, this term designates cash flow that's not part of an annuity. I should make this maximize this so you can see a little bit better. Okay, so we are asked what is the present value of this uneven cash flow stream in your exercise, and you can see here it's at 10%. In period 1 is $100, period 2 $300, period 3 $300, period 4 negative 50. Now this, you might be asking yourself, why would the cash flow be negative in period 4? A good example of this could be something like a nuclear waste site. So they'll make positive cash flows all along, but when they close up shop, they actually have to pay out money to clean everything up at a Superfund site or some sort of nuclear waste site. So it actually could be a negative cash flow in the final year. So this isn't unprecedented, but it is kind of rare to see something like that. Okay, so if we did want to obtain the present value, you could do so through typical mathematics, which you see here. And discount back, and I can do this in Excel. So I'm going to switch over to Excel. Bear with me for a second. I think I must have closed out of it. Oh no, I didn't. Okay, here we go. Yeah, there we go. It's a little bit better. So you could start out by putting in all of your CFs. So for CF 0, it's 0, and the cash flow in period 1 is 100. Cash flow in period 2 is 300. Cash flow in period 3 is 300, and cash flow in period 4 again is negative 50. So how would we discount each of these back? Well, you could use the formula, which you can see here. So you take $100 over 1 plus R or I, depending on what textbook you're using, to the first power. And that would get you 90.9. Here it's 300 over 1 plus R to the second power. That's 247.9. Here it's 300 over 1 plus R to the third power, and that's 225.3. And here it's negative 50 over 1 plus R to the fourth power, and that's negative 34. Spot 15. So if you sum all of these across, you get 530. An alternative way to do this is to write in equals NPV, parentheses, grab your rate, 10%, and then grab your values, 100, 300, 100, negative 50. As you can see, you get the same answer. This is going to be tricky though. I don't always suggest using this NPV function yet because we're going to be utilizing it in chapter 8 in a different way. So it might be somewhat confusing at that point, but it does make this type of problem a lot simpler. So something you can consider. Again, that's the NPV function, equals NPV. All right, let's go back to the slide set. And this is telling you how you could solve it using that NPV function. All right, moving forward, will the future value of a lump sum be larger or smaller if it's compounded more often, holding the stated interest rate constant? And that the case would be it would be larger, as there's more frequent compounding. Interest earned on interest happens more often, and therefore you're going to end up with a larger future value, as you can see here. There's if it's semi-annually compounded over 3 years. That's 6 periods of compounding. And that will make the value larger than just annual compounding over 3 years. The next section we're going to move into really talks about interest rates. It's a pretty detailed section. For your homework, you're going to have one question on this. I think I'll show you the formula in a second. But it's important to just walk through some of this information because, first of all, the text is going through it. And secondly, you might see some of this information if you pull out like a credit card statement or something of that nature. Okay, so let's start by defining the nominal interest rate. The nominal interest rate is also the quoted or stated rate. It's an annual rate that ignores compounding effects. It's also called the APR. So the nominal interest rate is typically stated in contracts. Periods must also be given. An example would be 8% quarterly or 8% daily interest. And we've been assuming this up until now. The periodic rate is different. It's the amount of interest charged per period, for example, monthly or quarterly. So the periodic rate would be the nominal rate divided by M, where M is the number of compounding periods per year. So M could be 4 for a quarterly, M could be 12 for monthly, that sort of thing. The effective or equivalent annual rate, EAR or EFF percent, is the annual rate of interest actually being earned, accounting for compounding. The EFF percent for a 10% semi-annual investment would be this formula here. So EFF percent equals 1 plus the nominal rate over that M variable to the M power minus 1. Now I know this is a complicated equation, but this is an equation that you have a homework question on, and it's pretty simple. Just plug the numbers in, and you should be able to get your effective annual rate. You should be indifferent between receiving a 10.25% annual interest and receiving 10% interest compounded semi-annually. So basically the effective annual rate is taking out the compounding and semi-annual components and making it more easily digestible so that you can make comparisons. So why is it important to consider the effective rate of return? Investments with different compounding intervals provide different effective returns. So to compare investments with different compounding intervals, you must look at their effective returns. Why is it important to consider them further? You can see how the effective return is going to vary between investments with the same nominal rate, but different compounding intervals. And you can see here that they're compounded more often. You see the rate increases. When is each rate used? The nominal rate is typically written in the contracts quoted by banks and brokers and is not used in calculations or shown on timelines. The periodic rate is used in calculations and shown on timelines. If M equals 1, the nominal rate is going to be equal to the periodic rate, and that's actually going to be equal to the EAR. The EAR is used to compare returns on different investments with different payments per year. It's used in calculations when the annuity payments don't match the compounding periods. Okay, moving on to compounding. I think you're familiar with this at this point. Annual compounding is the arithmetic process of determining the final value of cash flow or series of cash flows when interest is added once a year. Obviously, semi-annual compounding is that process when interest is added twice a year. What is the future value of $100 after 3 years under 10% semi-annual compounding? How about quarterly compounding? Here's our formula. Future value equals present value multiplied by 1 plus the nominal rate over n multiplied by m times n. So you have all your variables here. You plug them into the formula, solve it out. It's pretty straightforward. Again, m is how often it's compounded, n is the amount of time. So we already talked about the nominal interest rate. This is the contract or quoted interest rate. The annual percentage rate is the periodic rate times the number of periods per year. And the effective annual rate is the annual rate of interest actually being earned as opposed to the quoted rate. It's also called the equivalent annual rate. Can the effective rate ever be equal to the nominal rate? Yes, it can, but it's only the case if the annual compounding is used. In other words, if m equals 1. If m is greater than 1, the effective annual rate will always be greater than the nominal rate. Okay, the final aspect of this chapter is probably one of the most relevant parts of the chapter, other than the annuity section, because we're going to talk about loans. So anybody who has a mortgage knows all about this. We're going to talk about loan amortization. So we're going to actually create a very simplistic amortization table. Amortization tables are widely used for home mortgages, auto loans, business loans, retirement plans, etc. And by the way, if you hear something weird in the background, that's my dog. Apologize for that. Financial calculators and spreadsheets are great for setting up amortization tables. Your spreadsheet Excel is going to be an excellent tool for this sort of thing. So we can construct an amortization schedule using for a $1,000 10% annual rate loan with 3 equal payments. And that's what we're going to do going forward. This is in your Excel sheet. So if you scroll to the end, we have all the information here. Just make this a little larger so you can see it. And okay, so again, it's for $1,000, 10% annual rate loan with 3 equal payments. So step 1 will be to find your required annual payment. All the input information is given. Just remember that future value is 0 because the reason for amortizing the loan and making the payments is to retire the loan. So if we want to find our payment, we plug in our n, we plug in our interest rate, we plug in our present value, and we'd solve for payment. And that's what we're doing over here, solving for payment. So equals PMT, put in your rate, put in your number of periods, put in your present value, and put in your future value. You get 402. Okay. So we have $402. Step 2 is find the interest paid in year 1. The borrower will owe interest upon the initial balance at the end of the first year. The interest being paid in the first year can be found by multiplying the beginning balance by the interest rate. So take $1,000 times 10%, you get 100. So we know that that's the interest payment. So we also know the principal or the overall payment is 402. So we can calculate our principal payment by taking that overall payment of 402 minus that 100, and we'll get the principal payment of 302. So we put all of the above in the amortization table. We take that 302 and we subtract it from our beginning balance of 1,000. So here's our beginning balance down here. We calculated our total payment of 402. We know that 100 of that's going to interest, and we know that 302 of that is going to principal. Therefore, our ending balance is $697.89. We're going to do this entire process over again in year 2. We'll start with $697.89. We have our total payment of 402. Now our interest payment is $69.79, and our principal payment is $332.33. So real quick, just zone in on this. Notice what's happened. The interest payment has gone down, and the principal payment has gone up. So this is what they tell you, when you have a 30-year mortgage, that you're really just hitting interest at the origin of the loan. But as the loan goes on, you start to hit more and more principal, and that's what we're seeing here. So again, you started with 100 in interest payment and went down to 69. You started with 302 and principal payment went up to 332. Anyway, our ending balance at the end of year 3 is $365.56. So we start with that in year 3. Our payment is 402. 36 goes to interest. 365 goes to principal, and by the end of that year, we come down to a 0 ending balance. That takes us through the amortization table. And this is a slide just kind of reiterating what I was talking about in terms of interest and principal payments. At that point, we're done chapter 5, but I want to open up chapter 6 because I have one thing I want to show you from chapter 6 that's relevant for your homework. Bear with me for a second. I'll close out of this. I'll open up chapter 6. We're only going to talk about a very small section. can see here. It's very brief. And since you had macro, um, this section of chapter 6, we're gonna dive right into something that's kind of in the middle of the chapter. But since you've already taken macroeconomics, um, this should be somewhat relevant, and it'll be a good thing that you will be able to think about in terms of having some knowledge of what inflation is and how that would impact interest rates. So in chapter 6, we're going to be talking about interest rates and we're going to be talking about bonds. But in this particular section, we're going to talk about how inflation impacts interest rates. So a real rate of interest is the change in purchasing power. Nominal rate of interest is the quoted rate of interest. It's the change in purchasing power and inflation. So you've probably heard in your macroeconomics class that the difference between real and nominal. Real, I typically use this example for the difference between real and nominal. A real income, let's start with nominal income. Let's say your nominal income is $40,000 and you go into your boss and he gives you a 10% raise. And so you end up with a $44,000 nominal income. But let's say that inflation in that year went up by 5%. Do you make more than you did the year prior? Well, yes, you're making more in terms of nominal value, but is it worth more? And the answer to that is no, and that's why the real income matters. Real income is income adjusted for inflation. So if you are ever under the circumstance where you get a raise from your supervisor or boss and it's under the rate of inflation, your real income is actually declining. So that gives you an idea of what the difference between real and nominal is. So not only is real and nominal applicable to income, it's also applicable to GDP. It's also applicable to interest. So again, real rate of interest is the change in purchasing power. The nominal rate of interest is the quoted rate of interest, and it's the change in purchasing power and inflation. So the ex-ante nominal rate of interest includes our desired real rate of return plus an adjustment for expected inflation. So there's this Fisher effect, named for a famous economist. The Fisher effect defines the relationship between real rates, nominal rates, and inflation. As you can see here, we have this equation, which is 1 plus capital R, the nominal rate, equals 1 plus R in parentheses, which is 1 plus the real rate, multiplied by 1 plus the expected rate of inflation. And there's an approximation of capital R equals lowercase r plus h. So if you were given in your homework variables to plug into this equation, it should be pretty simplistic to just plug the variables into the Fisher effect equation and solve. And that's exactly what your homework is going to be like. So to give you a quick example, if we require a 10% real return and we expect inflation to be 8%, what's the nominal rate? Well, you could real quickly do the approximation, which is not completely correct, but you just add 8% to 10% and you get 18%. So that's this part down here, this approximation piece. 8% plus 10%. So this is the 10%, this is the 8%, you get your 18%, and that's the approximation of what you would get up here, but it's not precise. So if we want to be precise, we plug in all the variables. So going back to this, if we want to have R by itself, we'd have to subtract the 1 across. So it would be 1 plus R multiplied by 1 plus H minus 1. That's exactly what you see over here. 1 plus 10% multiplied by 1.08 or 1 times 0.08 and minus 1. And if you do the mathematics there, you end up with 0.188 or 18.8%. And because the real return and the expected inflation are relatively high, there's a significant difference between the actual Fisher effect and the approximation. And that would be important going forward. So interest rates are going to be pivotal for bonds. Inflation is going to impact the bonds. And in this section, we're just talking about how inflation is impacting interest rates. Next week, when we get into the bonds chapter, we'll talk more about how not only is inflation impacting interest rates will impact bond valuation. So we'll talk more about that next week. Talk to you then.